Good morning everyone. Today our group will be presenting our project for the Autotronic system service course. Our project is titled Automatic Headlight Dimming and Adaptive System. My name is Adi Sinuki and my teammate is Irfan, Awaridaudin and Naki Uzair. Our goal for this project was to explore how Autotronic component can solve real-world safety issue on our road today. To start, we must look at the global crisis of nighttime and road safety. As you can see in the high beam glare diagram on the slide 3, the main optical axis of a modern high beam bulb point directly into the tested driver in the line of sight. When a driver forgets to dim their light, it causes the Troxler effect or temporary flash blindness. This is a critical issue in 2026. As vehicular density has increased significantly, our objective is to design an automated system that removes human error entirely, ensuring that no driver is ever accidentally blinded by another.
Hello, my name is Muhammad Irfan bin Kamal Zaman. So I will present from slide 5 to 8. So for the slide 5 is technical explanation, smart beam and AFS. Moving into the technical core of the modern vehicle, we looked at smart beam and adaptive front light system AFS. Smart beam technology is essentially the vehicle vision, utilizing a CMOS camera mounted behind the rear view mirror to constantly scan the horizon. It is programmed to distinguish between the light of oncoming headlight and red light of the tail light. Component is the EFS, which is you can see at the diagram. The system is revolutionary because it doesn't just point the light off straight, it just a straight angle and speed sensor to physically pivot the headlight projectors. This ensures that the light follow the actual path of a vehicle during the turn, eliminating the viewing area where the driver actually heading. We go to the next slide. Technical explanation about matrix LED and masking. We have the matrix LED system, which represent the cutting edge of a 2029 and 2026 automotive lighting. As shown the advanced masking visual, the system allows the high beam to remain active all the time. Instead of turning the whole light off, it identifies the coordinate of oncoming car and vehicle being followed. Then selective dims only the LED segment that will hit those cars. This creates the dark corridor or a shadow box around the motorist, while the rest of the road, including pedestrian and road sign on the shoulder, remain brightly lit for the maximum safety.
Circuit design and operation logic. For our project prototype, we designed a circuit using a light-dependent resistor LDR as the sensor and an electromagnetic relay as the switch. The logic is simple but highly effective. When the LDR detects light exceeding 16,000 lux, its resistance drops sharply. This triggers a comparator and activates the relay to flip from high beam to low beam. The primary advantage here is speed. Our system reacts significantly faster than the average human reaction time of 1.5 seconds. Second schematic, LDR and relay. This is the schematic for our prototype circuit. You can see the LDR1 acting as our primary sensor connected to a transistor T1 that drives the relay. When bright light hits the LDR, it completes the circuit to the relay coil, which then physically moves the for contact from the high bright pin to the low bright pin. It's a simple, low-cost design that proves a robust solution for automated beam switching. This is our circuit schematic. Next, diagnostics and troubleshooting. Maintaining this system is crucial. Common issues we identify include sensor drift caused by UV or salt damage, which affects calibration. Physical obstruction like mud or dirt on the windshield can also block the sensor's view. On the electrical slide, relay coils can burn out from excessive switching, or ground connection can corrode due to rainwater exposure. A professional pro tip is to always check for aftermarket dash cams or stickers that might be blocking the camera's line of sight. Next, service and diagnostic guide. When servicing the systems, we follow a 3-step guide. First step, visual inspection. We look for lens fogging or moisture that scatters light. Step 2, multimeter testing. We verify that a 12-volt supply is reaching the relay pins. And the last, third step, systematic flow chart. We use a logic-based flowchart to isolate whether the fault lies in the LDR sensor, the wiring harness, or the relay itself.
I'm Aufaridauddin. So for the next slide, schematic flowchart. Now to make things easy for technician, we come up with the flowchart. It's a step-by-step way to find a fault. You start with the simple stuff, like checking if the sensor is just dirty. If that not it's, you move down the list to check the power supply and the LDR resistance. This yes or no logic help a mechanic fix the system quickly without guessing which part is broken. Real-time data and market analysis. We also look at some current data for 2025. It's turned out this technology is a huge deal right now. The market for adaptive lighting is growing at over 11% every year. This is mostly because new safety rules coming in 2026 are going to make smart headlight a standard feature in most new cars. So it's a circuit we are building today is exactly where the industry is heading. Market research visual. On this next two slides, you can see the chart we found from President's Research and Global Market Insight. They basically prove that more and more car companies are investing in semiconductor sensor, the same kind of tech we use in our project. It shows that even simply LDR system is part of a multi-billion-dollar shift toward safer, smarter driving. Conclusion. To wrap these things up, our project shows the automatic damping is a total win for road safety. It takes the stress of the driver and stop people from accidentally blinding each other. By using simple parts like LDRs and relay, we can make the road safe for everyone. That's all from us. Thanks for listening.